if you drop in and out of the network.
Do I need a link for that, or?
Yeah, it should just be any second. It's setting up your meeting for YouTube Live. It's connecting to my YouTube, and I'll pop the link in the chat.
Then I can.
But I'll mute the YouTube first, so I can't hear myself because it's very strange. Yep, I've got the link now. You can see us all.
Can you send me?
There you go. That's the YouTube link.
Okay. Yeah. Because I can put it on the research seminars page, which has a live feed. Yeah.
Perfect.
So in the moment,
I'll mute the YouTube first, so I can't hear myself because it's very strange.
Yeah.
Oh, right.
Yep. I've got the link now. You can see us all.
Frank, do you also want to put the slides into the chat?
I have done already.
Oh, have you?
It should be there, the link.
It's not in my chat.
Oh, not in the chat. Sorry, no, not in the chat. Just a moment. I will do it at the beginning.
Okay.
Yeah, any chat that happens isn't visible until people are in the call. So.
Oh, I see.
So if Sybil, if me and you were having chat, typing away before Frank joined, he wouldn't be able to see it.
Oh, I see. Okay.
Yeah.
Just quickly to add this. Just a moment. I need to. Okay. Right.
Sybil, all the beer gardens and whatnot reopen in Scotland next week, so I can imagine that we'll be following suit.
Yes.
Yeah, and it just popped up on my phone that Nicola Sturgeon's demanding that everyone wears masks in all shops now, because it wasn't up here. It wasn't mandatory.
I mean, I don't understand why they don't ask this, because I think there have been studies that show that if you are infected and you wear a mask, it really limits the spread.
Yeah, so public transport you have to up here, and I know that, but in shops,
I mean, in shops, I think it would make so much sense. I mean, because especially indoor spaces, you sort of, if you cough or sneeze, it projects everything. Right.
Right, that's just a minute too. I will share my screen and open the waiting room.
The waiting room. Okay.
I was just wondering, can you hear my voice well? Because I had some problems with my computer. Just want to make sure.
That's good.
Yeah, I can hear everyone.
It's good.
Right, okay, I'll open the waiting room and then share screen. There we go.
Okay, where was? Yeah, I need to. So let me put the. Okay, hope everyone is there, and welcome everybody for today's Lagoon, where we have Hiraku Nakajima. But before we start, let me just make some general comments about housekeeping as usual. So please, we will mute all microphones. Yeah, make sure your microphones are muted, besides the speaker, of course, and the chair. If possible, rename yourself so that we know who you are. Use chat function if you have any questions, and we will later, there will be time for answering questions. And but if you have some questions in between, please put them in the chat. And if you have any other questions, technological questions, you can also directly send a message to Liam from ICMS if there's some technical problems. And yeah, the next seminar will be actually next week at 4 p.m. So now the next slide, Liam, can you put the next slide? Yeah. So the next seminar will be on Thursday, 9th of July, and we will have Alexander Polishuk from Oregon. He will talk on geometry of the associative Young-Baxter equation. Remember, this is at 4 o'clock BST in order to give our speaker a chance not to do it too early. All right, and now I have Liam, can you put the next slide? Yeah, now it's a very great pleasure to welcome Professor Hiraku Nakajima from Kavli IPMU Tokyo in Japan, and he is going to talk about Euler numbers of Hilbert schemes of points on simple surface singularities and quantum dimensions of standard modules of quantum affine algebras. Hiraku, it's your turn now.
Okay, thank you very much for the invitation. Okay, I share the screen. So do you see my screen?
Yeah.
So I talk about Euler numbers of Hilbert scheme points on simple surface singularities and quantum dimensions of standard modules of quantum affine algebras. So this is some kind of continuation of Balazs' talk last month. He explained Euler numbers of Hilbert scheme points. But today I'm concentrated on algebraic part. And so that's the reason why in the title, I write Hilbert scheme in very small letters. And I'm concentrated on algebraic aspects of representation theory of quantum affine algebras. Okay, go to the next page. So let's get to be complex simple Lie algebra, and I assume this is of type ADE. And I denote UQ of G. This is quantized enveloping algebra, where Q is, I assume Q is not the root of unity. And I consider L of G, L of G, this is loop algebra. So this is affine Lie algebra without the degree operator, and the center is said to be 0. So this is a subquotient of the usual affine Lie algebra. Then I consider quantized loop algebra, and this is again subquotient of quantum affine algebra. Then we are interested in finite dimensional representations of this quantized loop algebra. More precisely, I'm only considering type 1 representations. So that is some technical terminologies. If you don't, if you are not familiar with this, just to ignore that we have some class of finite dimensional representations. And this category of finite dimensional representation of quantized loop algebra is known to be abelian category, and you have tensor structure because this quantized loop algebra is a Hopf algebra. But contrary to the usual finite dimensional representation of the complex simple Lie algebra or quantized enveloping algebra, this is not semi-simple. So in general, it is not decomposed into direct sum of irreducibles. And today, I also consider its restriction to finite dimensional category of finite dimensional representation of quantized enveloping algebra. So that is, as I mentioned, is a semi-simple abelian category. And it is this representation theory is basically the same as the representation theory of the complex simple Lie algebra, except this tensor category or braiding structure. And there's a fact which was proved by Drinfeld and Charlie Presley. So irreducible representation in this quantized loop algebra are parameterized by the so-called Drinfeld polynomial. This is a counterpart of the dominant integrable highest weight for the representation for this complex simple Lie algebras. So irreducible representation of A is parameterized by dominant integral weight. And similarly, irreducible representation in quantized loop algebra are parameterized by Drinfeld polynomials. And this Drinfeld polynomial is tuples of polynomials which has 0, which is equal to 1 at z equals 0. And this is a normalization condition. And large I is a set of vertex of linking diagrams. And for polynomial P, I denote by L of P for the irreducible corresponding irreducible representation. Okay. So go to next page. And so I introduced several important class of irreducible representations. The second one is not irreducible. The first one is called L fundamental modules. So this is an analog of fundamental representation. So choose I from the index set and A to be complex, non-zero complex structure, complex scalar. So then I consider the polynomial Pi of Z, which is equal to 1 minus A times G, and the Pj for other J, for J different from I is 1. Then this is a tuple of polynomials, and I consider corresponding irreducible representation, and this is called L fundamental representation. And I denote this by L of lambda I of A. Okay. Then for general P, so we have tuples of polynomials, and G, if we put G equal 0, it is 1. Then it factorizes to as follows, so like this. So PIZ is the product of 1 minus AI alpha Z. So AI alpha is basically roots of this polynomial. Then I consider the corresponding L fundamental modules and take a tensor product. And tensor product is in fact depending on the ordering. So you must be a little careful about order. So I explained the rule for the ordering here. So AI alpha divided by AJ beta is not the positive powers of Q on precisely powers which is greater than or equal to 2. And anyway, so this is some technical condition. If you put this condition and there is you order the fundamental modules in with this condition, then we consider the tensor product that it is called the standard module. So for any given module, you can order in this way, OS, and you can, and if this condition is satisfied, then the ordering is doesn't matter. So in that sense, the standard module is uniquely determined by a polynomial P. So I denote by M, standard module by M of P. And there are facts, there are several facts. One is any irreducible representation is a sub-representation of this standard module. So it is clear that this is irreducible representation sub-quotient, but in fact, this is a sub-representation. That is slightly harder to prove, but anyway, it is known by various peoples. And also, so you can compute composition multiplicity of irreducible representations in standard modules. So this MP.LQ is a composition multiplicity. So this number is given by the dimension of intersection cohomology of graded Kuiper varieties, which I proved some years ago. So this is some known facts, which will not be used later. And third fact, which I will use later, and in particular, it was used in the proof of the Jenge-Nemeth-Sendrois conjecture, was the following. So this, I mean, the second statement, this multiplicity is given by intersection cohomology. This is based on this third fact. And this standard module MP is realized as the equivalent K-theory of Kuiper varieties. And this, more precisely, this Kuiper variety of LVW, which is Lagrangian subvariety in M, which I usually denote by MVW. I take Dinkin diagram type ADE corresponding to the Lie algebra, and I consider the associated Kuiper variety, and its equivalent to K-theory realize the representation quantized to loop, corresponding quantized to loop algebra. And the dimension vector Wi is corresponding to degree of the Drinfeld polynomial. So in particular, if you restrict this standard module to representation of the quantized enveloping algebra. So this is corresponding to finite dimensional real algebra. Then its character is given by generating function of Euler numbers of this Lagrangian subvariety. So this connects the problem of the scheme points on singular surface and this representation of quantum loop algebra. Okay, so this is fact. And in fact, this result, as I mentioned as a second fact, this result gives us some way to compute dimensions of irreducible representations, but computation, because this is given by dimensions of intersection cohomology groups, but in practice, this is given as a combinatorial algorithm, which is very hard to use. So this, if you are familiar with Kazan-Lustig polynomials, then you may heard about this. Is you have some recursive algorithm to compute it, but it is in practice very hard problem. And this is sorry, maybe I must be a little bit more careful. So this intersection cohomology groups gives this composition multiplicity. So in order to compute the dimension, you also need to know the dimension of the standard module. So this is two steps. First, you know the dimensions of standard modules, and then characters of standard module, and then you need to compute composition multiplicities. And I explained the first part. First part is something like Kazan-Lustig polynomial, and it's difficult. And also character of standard module has algorithm to compute. So this is computation of Euler numbers of Quiver varieties. And this second algorithm is also recursive, and actual computation is very hard. So it's really, in general, difficult problem to compute explicitly, compute these explicities. But if you restrict yourself to a special class of irreducible representations, so this is not arbitrary one, special class, then we have simpler algorithm, which is much easier to handle. So this happens, and this special class includes the so-called Kirillov-Lechetsky modules. So this is some special class of irreducible representations, for which we have better understanding. We have better algorithm to compute the characters. So I will explain what are the Kirillov-Lechetsky modules. So this is a special. I mean, I explain the corresponding Greenfield polynomial, and that is fine. But somehow you don't see what kind of structure it is, what kind of module it is. And for type A, it is known that Kirillov-Lechetsky module is a lift of the irreducible representation of finite dimensional UQ of G, UQ of G. But in general, it is a little bit more mysterious, and you must add, you cannot simply lift to the representation of quantum enveloping algebra to quantum loop algebra, and you must add some smaller representation to the highest and to the irreducible representation, and that is some difficult part of this case. But because, as I said, there is some simple algorithm, and one can slightly better understand. So anyway, let us explain. So it is assigned for I, the vertex of linking diagram, and positive integer k, and non-zero scalar a. And I denote the Kirillov-Lechetsky module as double I of Ka. So this is an irreducible representation quantum loop algebra, whose Greenfield polynomial is given by this formula. So for J, if J is not I, this is just 1. And if J is equal to I, then starting from 1 minus AG, I multiply Q square, and so on. And finally, for given K, I multiply the last factor as 1 minus A times Q to the 2K minus 2 times Z. So this is degree 2K, degree K polynomial. And the first one, if K equals 1, then I only have this linear function. So this corresponds to fundamental modules corresponding to vertex I and scalar A. And if K is equal to 0, I understand the double 0 of IA to be trivial representation. So this is as for convention. Then one of the nice feature of this Kiddo-Fletcher scheme module is the so-called Q system. So I restrict Kiddo-Fletcher scheme module to the module of UK of K. So this is restriction. And then I compute its character. So I denote it by QIK. Then QIK satisfy this recursive relation. So I take QIK of square, then this is equal to QI of K plus 1 times QI of K minus 1 plus QJ of K, where J is running to vertices, which is connected to linking diagonal with I. In fact, this comes from some short exact sequence of this Kiddo-Fletcher scheme modules, but I will not explain it today. So anyway, so this can be regarded as recursive equation. So starting from K equals 0 and 1, so K, you just put the K equals 1, then you only have a single term with QI of 2. So K plus 1 becomes 2 if K equals 1, and all others is Q1. So you can determine Q2 from Q0 and Q1. And similarly, QIK plus 1 is determined from previous terms. And people understand this is mutation relation in the cluster algebras, and people understand the relation between these Kiddo-Fletcher scheme modules and cluster algebra. For example, Francesco Kedem, Hernandez Clark, and others. So in particular, using this cluster algebra technique, Francesco Kedem gave a proof of the so-called Kleber's algorithm. So Kleber introduced some algorithm to compute this character, namely this QIK. So his expression involves some binomial, Q binomial coefficients and some explicit form. In practice, it's a little difficult to compute, but so anyway, so he gave a simpler algorithm known as Kleber's algorithm, and he assumed that he assumed various things, but somehow this assumption was later proved by this Francesco and Kedem. Okay. Let me continue. Yeah, so as I said, this is much simpler than the computation of intersection. So this is simple recursion. So this is much simpler to compute to this recursion, except I mean, so as I said, you need to also know that this first term, and the first term is in general already complicated. So in that sense, this recursion not, but Kleber's algorithm also gives this the first term. Okay, let me continue. So next, I will explain quantum dimensions. So this has been introduced by Anderson in his study of the quantum enveloping algebra at roots of unity. So I mentioned that quantum enveloping algebra has basically the same representation theory as finite dimensional real algebras, representation theory of complex simple real algebras. But that is true only for when Q is not the root of unity. And when Q is a root of unity, it's much more difficult and much more subtle, and it is somehow connected with the representation theory of the relative groups in positive characteristic. So it's very interesting subject. Anyway, he introduced the notion of quantum dimension, and it plays some role in the definition of the not invariant by reciprocating twice. So anyway, so the definition is something simple. So in fact, you don't need to start with the representation of quantum enveloping algebra. You just need to have a representation of the real algebra. So let V is a finite dimensional representation of the real algebra, okay? Usual one. And I consider its character. So this is the generating function of dimension of weight spaces. And so this is given as a polynomial in exponential of alpha I, or exponential of minus alpha I, Laurent polynomial, yes. And then I take zeta, which is a root of unity. Then quantum dimension of V is given as a specialization of this character at some root of unity. You just put all the exponential of minus alpha I, or maybe you can put also exponential alpha I. That gives the same answer. So you just specialize exponential of minus alpha I to be zeta, this root of unity. This is the definition of quantum dimension. And I mentioned this appears in the context of the representation theory of quantum enveloping at root of unity. And if V is irreducible representation of J with highest weight lambda, you have some analog of wild dimension formula, which is rather easy to show by using the usual wild character formula, and just to take the limit of the wild character formula. So this is some product of fraction, and denominator is zeta to be this zeta to the power low here with alpha check. Alpha is positive roots, and rho is half sum of the positive roots, and alpha check is corresponding co-root. I mean, we are just only considering AD, so there's no distinction in co-root and roots, but as a combination I do in this way. And numerator is just different, that rho is replaced by lambda plus rho. And if this is strictly speaking, this is true only when the denominator doesn't vanish. And this is very mild condition that this is not. If zeta is the powers of zeta is not too small powers of unity, it is true. Okay. Then I use the following notation. So zeta integer or q integer, where q is taken as roots of unity, is equal to this one, zeta n minus zeta to the minus n divided by zeta minus zeta inverse. So this is just a simple replacement of this formula, but somehow you will see that the right ink is somehow more illuminating. Okay, this is quantum dimension. I will not go to I will not explain any background for this quantum dimension, and I just mentioned that it's something to do with roots of unity. But if you are interested, just to look at Anderson's paper or some literature in the representation theory of quantum enveloping algebra at roots of unity. This is an interesting subject, but I don't go into detail. Okay, so next. So I will explain Kuniba's conjecture, which go back to 93. So this conjecture was made before cluster algebra was introduced. So I will come back to cluster algebra later. So take positive integer L and take specific roots of unity. So this is exponential of 2 pi I divided by 2 times h check plus L. So this is even roots of unity. So for not invariant, people usually consider only odd roots of unity, but at least for quantum dimension, there's no distinction. Or maybe for even case, I mean, as I will explain later, something interesting will occur. And H check is dual Coxeter number, but it's same as Coxeter number because I assume this G is type AD. Then I consider Kirchhoff-Lechesky module, and then I restrict to quantum enveloping algebra, and I consider its quantum dimension. So this is the one which I'm interested in. So this is a specialization of the character of the restriction Kirchhoff-Lechesky module. And the claim is this is periodic with period L. Oops. So when L is equal to, when K is equal to 0, by convention, I understand this double I of 0 A is trivial representation, and its quantum dimension is just 1 by definition. But if if I assume this is periodic, then if K is equal to L, then it is the same as the quantum dimension of trivial module, which is equal to 1. So this is a statement. And this is I mean, you return back to the Q system. So as I said, you start with this starting from Q0 equal 1 and Q1 something. Q1 is something given. Then you can solve this recursion. And in general, if you just consider the ordinary character, then it grows. I mean, of course, this is the character of representations, and representations become larger if K increase. But once you consider this quantum dimension, then something very funny happens. So if L equal K becomes L, then you return back to something trivial. So this is very surprising statement. And similar phenomena is observed for quantum enveloping algebra at roots of unity, but this statement is much simpler. I mean, still in the quantum enveloping algebra at roots of unity is something more complicated, but this is rather striking, at least for me. And in fact, positivity of characters and many more nice property are expected. And if you are interested, I just only stated the main part. And if you are interested, just look at Kuniba's paper. I think this is interesting. And this conjecture was proved for type A. Type A case is relatively easy. Kirchhoff-Lechesky module is just the irreducible representation of the usual finite dimensional complex D algebra. Or I mean, this is exterior power in practice. So because this is type A, and I is fixed, and K basically this is K times fundamental representation for I. So this is so you must, so this is the first one, and you must take tensor product. So anyway, so this is correspond to rectangular Young diagram, and you can write down the character explicitly, and you can directly check. And for type D, Kirchhoff-Lechesky modules are not really irreducible representation of the quantum enveloping algebra. You must add some smaller representation, but this smaller representation is known. I will explain for K equal 1 later. And it was used by Lee to check this periodicity for type D. And for type E6, it's slightly little bit more complicated, but somehow, at least for some special, most of the vertices I, except the triple node one. The characters are known. This decomposition of this restriction are known, and it was used by Glide to check this conjecture. Okay. Well, somehow these proofs are basically based on some explicit knowledge of the this Kirillov-Lechetsky modules, and I mentioned that this character is in general computed by Kleber's algorithm, but Kleber's algorithm only Kleber's algorithm is in general just algorithm. So if you are considering the linking diagram, for example, triplet node of the E6, E7, E8, then explicit character of this restriction Kirillov-Lechetsky module are not known. Just you only have just algorithm. Okay. Then main theorem, which I will state now, is this conjecture is true for L equal 1. So if I state in this way, this is not a difficult theorem at all. It is just a checking, so I will explain in the next page soon. And the point is, as I said, Kleber's algorithm is complicated, but for L equal 1, you can compute the algorithm. You can really have explicit formula. Then I just substitute this root of unity, and I check this is equal to 1. And but this is somehow useful to prove this conjecture by GNS about Euler numbers of Hilbert-Scheme points. And this is first because for L equal 1, as I mentioned, this Kirillov-Lechetsky module is nothing but fundamental representation. So fundamental representation is a tensor product. Standard module is a tensor product of L fundamental representations. So once you know that this quantum dimension is equal to 1 for fundamental representation, all standard modules have quantum dimension 1 because this is just tensor product. Okay. And so this general conjecture on Hilbert-Scheme, Euler number Hilbert-Scheme, follows from this equality of triviality of the standard modules, because as I explained, this character is connected with Euler numbers of the quiver varieties of finite type. And I think already Balash explained that, so starting from, so this Hilbert-Scheme is something to do with quiver variety of affine type, but you have a projective morphism from the quiver variety of smooth quiver varieties of affine types to Hilbert-Scheme points, and the fibers are quiver varieties of finite type. And once you know, have a good understanding of Euler numbers of the quiver varieties, in particular this specialization, then you can say something on Euler numbers of Hilbert-Scheme points. So this is a geometric part, but I will not go into detail. Okay, now it comes to fun part, and I explain how I check this theorem. So this quantum dimensions of this fundamental modules. So since I'm considering L equal 1 case, this is fundamental representation, L fundamental representation. So now I explain how I check this conjecture. So I started with type AN-1. So in this case, it is known that the quiver variety, corresponding quiver variety, is either empty set or single point. And that corresponds to the fact I already mentioned several times. So this Kirillov-Lechetsky module is irreducible representation of finite dimensional algebra, and you don't need to add any smaller representations. And geometric reason behind this fact is this triviality of quiver varieties. Quiver varieties either empty or single point. Then the character no, quantum dimension is same as this zeta binomial coefficient. I mean, if zeta equal 1, this is exterior power, dimensions of exterior powers, which is just binomial coefficients. And if you consider quantum dimension, then you just replace usual binomial coefficient by zeta binomial coefficient, which is by definition. So you have, it's written by fraction, and numerator starts from n and n minus 1 and so on up to n minus I plus 1. And the denominator is starting from I and I minus 1 until 1. Then remember that zeta is n plus 2n plus 1 root of unity. And this is even order roots. And if I consider power zeta to the power n plus 1, then this is equal to minus 1, right? Then I compute n plus 1 minus k zeta integers. Then this is by definition minus, because this is minus 1, minus to the power zeta to the minus k plus zeta to the k. This is numerator, and the denominator is zeta minus 1. And this is equal to the zeta integer k, right? By definition. So if you are in positive characteristic, then for characteristic p plus m, p is equal to 0. But here we are living in the, so this, you have good analogy with this for the zeta integers. But if zeta is even order root of unity, I mean, that could not be positive characteristics. But here, n plus 1 minus k is equal to k in this world, in this zeta world. So then you look at this fraction, and you see that n and 1 cancels, n minus 1 and 2 cancels, and so on. All the numerators and all the denominator cancel, right? So you get 1. I think this is very remarkable. And it is true that this the assertion is true for type A and minus 1. Okay. Next, I will explain type Dn case. And again, maybe return back to this one. So you have this kind of expression is available because I explained this analog wide dimension formula. So you have the product over all the roots, positive roots, and many already cancelled, but like in this case. But anyway, so in general, we do have this kind of expression. And using this kind of expression, you can easily compute the quantum dimensions of the small representations. So for example, if you consider type Dn, this is SO2n. So this exterior powers, ith exterior power is irreducible representation, and you can just compute the corresponding quantum dimension. And you find that if I is equal to 1, so this means the 2n dimensional vector space, then quantum dimension is equal to 1. And if I is greater than 1, then it just 0 becomes 0. So this is something different from type A. And if you compute the quantum dimension of positive or negative spinor representation, this is 1. This is also easy to check. Then, so somehow the situation is different from the type A. So for type A, all fundamental representations have quantum dimension 1, but here it is they are not. But somehow this is compensated by the fact that type D Kirchhoff-Lechitsky module or fundamental representations are not irreducible as quantum representations of entropy. So the restriction of the fundamental module has the leading part is this one, ith exterior powers of of vector representation. But in order to lift it to the representation of quantum group algebra, you need to add smaller representation, as I mentioned several times. In this particular case, you add I minus 2 x to x to the power and I minus 4 x to the power. So you jump by 2. So depending on the parity of I, so it ends with the first once the vector representation or trivial representation. And I mentioned that if I is equal to 1 for vector representation, quantum dimension is 1 and the others are 0. And the trivial representation I didn't mention, but the trivial representation is of course having quantum dimension 1. So in both parity of I, so the final piece have quantum dimension 1, and all higher exterior powers have 0 quantum dimensions. So this restriction of fundamental representation have quantum dimension 1. And for spin representation, it is known that you don't, I mean, in fact, it is also known that the corresponding quiver variety is either point or empty. And this representation, just spin representation, just lift to the representation quantum loop algebra. So this is a irreducible representation. And as mentioned, this spin representation has quantum dimension 1. So in this case, the assertion is true. So somehow the reason for which quantum dimension is equal to 1 is very different for type A and type D. So in that sense, I just checked that the assertion is true, but somehow I don't see any conceptual reason why this is true. So if you go to type E678, then you look a bit more exotic. So let me explain. So in in 2006, so I said that I have an algorithm to compute Euler numbers. And in fact, as I mentioned, this is a very complicated algorithm. And even for this very fast one, I need to use a supercomputer. And for E8 and for triple vertex, this fourth vertex, this is most complicated vertex, and it took 350 hours for by supercomputer. And I needed quite a lot of memory. I don't remember how many gigabytes, but it was quite a lot. And I mentioned that the clever algorithm is much simpler, but still the formula itself, I mean, if you compute this character for this vertex, the first this fundamental representation, even for fundamental representation, Clever's formula looks very, very complicated. And I don't see any pattern for this, and I don't think any simpler formula for this. So anyway, you can compute, using Clever's algorithm, you can compute corresponding quantum dimensions and take some sum, and you get the assertion. And this is an example for this triple node. And well, this is a fundamental representation, in fact. Yeah, it's the same as standard, but L fundamental representation for this and for fourth node, and I restrict it to the representation quantum enveloping algebra. Then it decomposes into direct sum of finite dimensional representation modules of finite dimension quantum enveloping algebra. So this is the same as the representation of the usual complex simple algebra. So I used the notation from the complex simple algebra. So this lambda 6 plus lambda 8 denotes the highest rate. And this representation appears with multiplicity 4, and the second one with multiplicity 18, and Third one with multiplicity 23, and the trivial representation appears multiplicity with 10. And I don't have a space to write all other representation. In fact, there are lots of other representation, but all have quantum dimension equal to 0. So I can ignore them. And then I compute corresponding quantum dimension restriction of fundamental representation. So this is a final expression. So I compute this the quantum dimensions of this representation by using this wild dimension formula, and I found this to be -1. So dimension in general, because this is some specialization character, dimension could be negative numbers, and this is -1. And the second one is dimension 1, and third one dimension -1, and trivial representation is of course dimension 1. And then you compute this sum, 4 times -1 plus 18 times 1 plus 23 times -1 plus 10 times 1. And I compute it to be 1. So in this way, you just show that all the representations of all the fundamental, L fundamental representation of quantum loop algebra have quantum dimension 1. So this seems to be very miracle. And in fact, I first thought that all the quantum dimensions should be 1 or 0. So I didn't know that the possibility to be -1. And I little surprised when I found this is -1. But anyway, I don't see any theoretical background why this miracle happens. But somehow, as I mentioned, this so this Q system is a key point to connect the representation of the quantum loop algebra and the cluster algebras. And this periodicity appears in the cluster algebras in works of Keller and his collaborators. And this is a solution with this L-restricted Q system, and there's some way to understand this by representation theory of some algebras. So I mean the additive categorification of the cluster algebras. So I hope this suggests that this key of this scheme module still have some connection to cluster algebras, and this conjecture in general should be attacked in the framework of cluster algebra. So now I stop here, and thanks for attention.
Yes, thank you very much for the very nice talk, Yaku. So maybe we can just unmute and clap for a moment or put our reactions. If there are any questions, maybe people can just unmute and talk, or otherwise give me a sign in chat or raise a hand in participants. I will monitor or try to monitor all of it. So if somebody is want to ask a question, please go ahead. Yeah, there is a question by Pierre-Guy Plamondon.
Yes.
I see your hand is raised. Yeah, you want to go ahead?
No, this is the clapping hand. Sorry.
Oh, okay. Oh, yes, I can see that.
Okay, maybe I'll ask a question if that's all right.
Go ahead.
Yeah, sure.
So if I think of this from the quiver point of view, then you have level 1 representation. So it's framed at the trivial vertex, at the 0 vertex. So it's the usual story. You get level 1 representations of the affine Lie algebra. And then somehow your story, that level switches to 0. You kill the center. These finite dimensional representations. So do you have a conceptual reason at what point do we switch from level 1 to level 0, or why does it happen? I don't really deeply understand this still.
Well, I mean, I don't see any connection between the representation theory of positive level and the level 0, but my viewpoint is just as you already explained. So this, in view of this for this problem, so if you study the, if you try to relate quiver varieties of affine type smooth one and Hilbert scheme of singular surface, then fibers are quiver varieties of finite type. So this is the connection. And somehow for quiver varieties of finite type, the most natural, most powerful tool to analyze its structure is the representation theory of quantum loop algebra.
So once again, the loop, I shouldn't think of the loop as coming back from the affine. It's a different kind of loop. It's
a different loop.
Yeah.
And if you consider if you stay in the quantum affine, quiver varieties of affine types, then you have quantum toroidal algebra. You have two loops, and these two loops are very different.
Okay, but right. I mean, I guess fundamentally, I'm still confused because you kind of have this very beautiful story where you take representations of G hat, and then you go to these specialized stability conditions, you get kind of restrictions of representations to G, but that seems to play no role in this story somehow. You're saying that basically you look at this projective morphism, you have the fibers, they are finite type quiver varieties, and then you just organize those with respect to this other loop, and the two worlds don't seem to interact at all. Is that kind of what you're saying now?
Well,
so in other words, you're really only using the branching paper, your branching paper 10 years ago to understand that point. You kind of forget about that representation theory, and you kind of turn to this different one, which is the UQLG, which is organizing.
Well, maybe as I mentioned, that maybe you should start with the representation theory of quantum toroidal algebra. Then somehow this should give more unified viewpoint. And I didn't take this viewpoint, and I'm not sure this is a good point. But maybe if you insist some unified viewpoint, that might be first candidate.
Yeah, sorry, I don't want to insist on anything. It just strikes me. Yeah. No, okay, thank you. No, but that's thank you. That's good.
Yeah, many people study the representation theory of quantum affine algebra, quantum loop algebra, and many things is known. But not so much is known for quantum toroidal algebra. People think that quantum toroidal algebra is more difficult.
Sure. Okay, thanks.
I can see there's another question by Kevin McGarty.
Yeah.
I just wanted to ask, don't all these Kirillov-Reshetikhin modules have crystal bases? They're in Kashiwara.
At least for classical types, it is known.
So is there any kind of combinatorial or crystal theoretic version of these conjectures, or is it something that you think is not related to that?
That direction I don't consider, but this is a specialization of characters, so I'm not sure this is something good with crystal basis. And also, for the crystal basis, the difficult point is, so I just only consider that it's Kirillov-Reshetikhin module as a representation of quantum enveloping algebra. And for this crystal, the difficult point is to understand this Kashiwara operators for zero vertex.
Yeah, exactly.
Yeah, so you have starting, for example, type A. So you start with this Young tableau, and you must invent the rule for the zeros Kashiwara operators, and that is usually difficult. But as for, I don't know.
It was just a curiosity that whether some structure on the crystal might reveal that you should have this specialization at roots of unity or something.
Yeah, but I cannot imagine anything like, I cannot imagine such story.
But that sort of relates to my question in some sense, because our proof for A and D of the conjecture was very much, you look at the affine crystal and you make these substitutions, and this collapse happens.
I see.
So somehow the expressions you write at the end of the day look kind of curiously similar, although not exactly the same. You know, we used the same kind of story. So I mean, there must be some story which connects these 2 points of view, because we start with the affine Lie algebra representation just combinatorially through its crystal basis, and not just in type A but also in type D, so sort of uniformly. And then we make this substitution, and somehow this big collapse happens that, you know, lots of things cancel out, and then you count exactly what you want to count. And again, it's sort of miraculous in the same way that your calculation is miraculous. But that very much is driven by the crystal story. So
okay, yeah, I remember your work. And so this is so in this way you can connect the level 0 representation and the level 1 representations. So that is this path model. So basically you start with finite dimension representation, for example, Kieser-Brzezinski modules, and you consider the semi-infinite tensor product, semi-infinite exterior powers, and then you can realize positive level representations, and crystal basis of this positive level representation can be constructed from this crystal of these Kieser-Brzezinski modules. That was done long time ago by this Kashiwara and others. So this is path model, and Kam made it very explicit in terms of Young diagrams, Young tableaus. Yeah, that is a connection, and yeah, that might be a good viewpoint. But again, this quantum dimension is a specialization of characters, and this miraculous cancellation happens only by just computing this quantum dimension. So in the level of basis, maybe it is a little difficult to see this cancellation. Yeah, I don't try, so I don't know.
Thank you.
Are there any more questions?
I have a naive question. Is there any geometric interpretation of this Q is root of unity, this exponential 2 pi I over 2h plus 1 for this identity?
In my viewpoint, there is none, but I mean, the ordinary, this is, as I mentioned, this is related to quantum developing algebra to roots of unity and this is the usual story that appears in this definition of not invariance, or three manifold invariance.
Yes.
So you consider so you use this roots of unity. I mean, that is connected to, if the order of roots of unity is k, then that corresponds to the k minus h check level affine Lie algebra at level k minus h check and k plus h check, and that connects to Simons at level k. That is some geometric story, but this is very different from the story for equivalence.
But why k has to be 1 here?
Well, that is a numerical check, so I computed, and okay. I don't have any conceptual reason, and if I have, I can solve the conjecture in general.
I see. But for instance, can you generalize this whatever conjecture, I mean your theorem, to the like a higher rank instant on modular space, like instead of Hilbert scheme? I don't know. I mean, just naive question.
Yeah,
does it make sense?
That is an interesting question. I mean, instead of Hilbert scheme points on singular surface, you can consider similar program for instant modular spaces.
Yes.
And
okay, nobody.
I mean, I listed L equal 1, but I don't study, so I don't know.
Okay, thank you very much.
There's some little progress on that.
Oh, really? Good.
Okay, any more questions? That seems not to be the case. Then let's thank Hirako again for a very nice talk. And
thank you.
And thank you everyone for coming. Just to let you know, next week we start at 4 o'clock with a talk by Alexander Polichuk.